Hello physics students. Today we're going to be analyzing something that physics books like to call inclined planes. But really all it is objects that go down a hill. So basically this, I got a car with nice low friction wheels and I'm going to put it on a hill and then I could just let it go and watch it accelerate. Now just a little side note, if I were to ask you before today, is this a complicated thing? Most people who haven't studied physics would say, no, that's not a complicated thing. That's just a thing going down a hill. So we've got a simple situation, and we're going to analyze it with a simple law, Newton's second law, A equals F net over m. More force, more acceleration, more mass, less acceleration. And we're going to find that the simple situation with the simple law becomes very, very complicated quickly to analyze. So that's a bit of a warning. This is going to be a little on the challenging side, just to get you ready. So why is it challenging? Well, let's take a look at this. First thing, why does this go down the hill in the first place? We need a force, and yet I'm not pulling it, right? I'm just letting it go. So some of you might be saying, well, of course the force is gravity, the earth, right? And that's true. We're going to see that that's true. But here's an interesting thing. Why is it, or how is it, that this can go down the board when gravity doesn't act this way? Gravity doesn't pull down the hill, right? If I just drop this in the air, I won't because it's expensive, but it falls straight down. So that's planet Earth pulling it straight down. Now, I put it on a hill, and what happens? Does planet Earth suddenly look up and say, oh, now he's got it on a hill, let me pull it sideways or on a diagonal like that instead of straight down? No, it doesn't, right? It just keeps blindly pulling straight down. So we've got to figure out how that straight down force causes motion like this. And also, there's patterns here that emerge that we need to understand. Why is it when I let this go, we have a small acceleration on this hill, and then when I put this steeper like this and let it go, we've got a larger acceleration, okay? So we've got to be able to understand that and then analyze and calculate that. And then we could even add something without wheels. And now notice, it doesn't move now. Why? What about now? Can we analyze its acceleration as it slides? Now we have another effect, the force of friction. So lots of complicated things to understand. The first thing we're going to do is just take a look at the forces involved of something on a hill and try and get some understanding of what's going on. So here are here's the beginning of the notes for the day. Let me just explain some things before you start copying. So here's the title, Objects on a Hill. So the three forces that act on something on a hill. So I draw the hill here, and I try to draw it lightly so the arrows stand out because like all Newton's laws problems, it's the forces that matter. And so the hill here, ideally I wouldn't even draw it, but I want to draw it just lightly to get my mind into thinking about that the hill is here affecting this. So here we have the force of gravity, like always, it's mass times 9.8 straight down toward the center of the earth, okay? The normal force is here to prevent this block from breaking through the board. If I put like a really weak board and maybe I put like 1,000 pounds on it, the board would snap and it would just fall right through it. But the board has integrity. If it doesn't snap, it's going to prevent this from going through, but the normal force it creates is always perpendicular to the surface. So I recommend you take something to guide you, like a sheet of paper, and you see what I've done? I've used the corner of the sheet of paper to truly draw this force perpendicular to the hill. A lot of times people do like this or they go like this. So truly perpendicular, use the paper. And then force of friction. If this is sliding down the hill, friction is up the hill. So this should be parallel to the hill. So those are the three forces. And one final point, the normal force is shorter than the force of gravity. That's something we're going to find. So draw it a little bit shorter than the gravity force. All right, so let me pause now, give you a chance to copy this down, and then I'll go over it. Okay, so first point, the force of friction may be zero. Like in the case when I had the car with wheels, the wheels removed the friction, pretty much, all right, not exactly completely, but pretty much removed it. So sometimes there are only two forces, and this force would be gone, and the force diagram would just be gravity and normal force. Another point, if friction is large enough, the object may stay at rest. We saw that when I first put the box on top, it didn't move. That's because this friction is large enough to keep this thing rooted in place. But if friction is large enough, it may also cause the thing to slide down at a constant velocity. Both of these situations, remember, are net force zero, zero acceleration. Staying at rest or moving steady, same looking force diagrams. You can't tell the difference from just the force diagram. Force is balanced in both situations. I also already mentioned the normal force is not equal to the force of gravity. We're going to find that it's going to be the force of gravity times the cosine of this angle of the hill. So at 0 degrees, cos of 0 is 1, so it is this on a 0 degree hill, in other words, a flat surface. But the cosine function, as theta gets bigger, gets smaller, so normal force gets smaller. And then this is basically saying a lot right here, the pattern. As the angle of the hill goes up, the normal force gets smaller, and therefore the force of friction gets smaller, because normal force of friction is coefficient times normal force. The x component goes up, meaning the acceleration goes up. What do I mean by the x component? Well, what we have to realize is this gravity pulls this down, but we can think of it as having components. And if I draw a right triangle like this with the force of gravity, and I'll do it lightly so I don't clutter up the diagram, and I label this the x component of gravity, this being the theta of the hill, and this the y component of gravity. Now you might be saying, wait a minute, x should go this way. Why is x suddenly going that way? We do that because the problem is hard enough, so we allow ourselves to tilt the axes to line them up with a hill to make it a little more simple to analyze. So our x-axis is like this, and our y-axis is like that in an incline problem, okay? So this x component, this piece of this triangle right here, is what causes the acceleration. And as the hill gets steeper, this side gets bigger and causes more acceleration in the forward direction. And the last point, kind of, you may have not realized this, but it's obvious if you think about it. The steeper the hill, the faster the acceleration, the larger the acceleration. But the fastest you can get is a hill that goes straight down. That's like skiing and jumping off a cliff, right? You're just going to go 9.8 like that, right? So that's the most you could get, is when the hill is straight up and down. In other words, there's no hill, it's a cliff, and then you just fall within the 9.8. So a lot of information here and concepts about that force diagram. All right, so are you ready to give a shot at solving a problem and determining the acceleration of something on a hill? Well, whether you are or not, here it is. So here's our example. So let me read it quickly, and then I'll give you a moment to catch up and jot it down. So we got a 4-kilogram wood block sliding down a, oops, I lost the word, a wood board. Okay, a little scrunch there, sorry. A wood board at 30 degrees. And we're going to determine the acceleration, okay? So a lot of calculating coming up, okay? So as we always do, we draw a force diagram with all Newton's laws problems. I made the hill as light as possible. If you had a pencil, just sort of lightly graze an approximate 30-degree hill, right? 45 goes like, you know, like this. So a little bit less than 45, just kind of visualize it. Or if you really want, you could draw with a protractor. And here's the hill steepness, 30 degrees down here. We draw the gravity straight down. And remember, this 39.2 is not important. This is important, labeling it FG right here, okay? But the 39.2 I got from the 4 kilograms times 9.8. That's where that came from. And then I have my normal force and friction because I've got wood on wood, and that's not a frictionless surface. So there are the forces. The other thing is draw this on the shorter side. Don't draw it too long. draw a nice little short force of friction, because if you draw it too long, you're going to be implying that it's staying at rest. All right, so go ahead, and if you need a moment, I'll pause to let you catch up with that diagram. Okay, so now comes the solving. So what we have to do is find the portion of this gravity going down the hill. So what I can do is make a right triangle out of my gravity vector. I can use a corner of a piece of paper like this, and I'm going to slide it down until it meets this end of the arrow right like that. And there, right there, I've got a triangle, right? There's my hypotenuse, and then the legs are over here and over here. So let me sketch that in lightly, like that. And like this, so going down the hill. This is my 90-degree angle. This is what we call the X part of gravity that's pulling it down the hill. This is what we call the Y part, Fy, and our 30 degrees goes right here. So before we even begin, we need to find the lengths of those. And we could do that because it's a right triangle with the sine and cosine function. So let me begin by finding the y component right here. This is next to the angle, so we say it's the adjacent side. And this is the hypotenuse opposite the 90-degree angle. It's a little tricky because our triangles kind of flip to the side. So I'll begin with writing out the cosine function. Cosine theta is adjacent side over hypotenuse. And so now I'll plug in my numbers. Cos of 30 equals the adjacent side, which is the y component, okay? And the hypotenuse is the 39.2. Okay? Now, I need another line over here. I'm going to move over there. But before I do, I just want to also start the calculation for the x component. This is the opposite side, opposite the angle. So the trig function we use is not cosine, but sine this time. So let's say the equation is sine theta, and it's the opposite side, so we still need a formula, as always, over the hypotenuse. And now we can plug in our numbers. Sine of 30 is equal to the opposite side, which is x, over 39.2. Okay? All right, so now I'm going to make some room here. I'm going to erase this board so we can continue. Okay. All right, so if you need a moment, let me create a pause so you can catch up if you need to. Okay, so this one, we can multiply the 39.2 over to the cosine, so we get Fy is 39.2 times cos of 30, which comes out to be 33.9 newtons. So Fy equals 33.9. Actually, let me do it a little more to the left. Utilize all the board space. And the sine part here of this calculation, I moved the 39.2 with the sine of 30 to get the x component of gravity. And 39.2 times sine of 30 is 19.6. Okay? Now, this basically is the forward thing that creates the acceleration. But in order to find the acceleration, we also have to factor in the friction because it's removing from the forward force. So to calculate the friction, I need the normal force, and this turns out to be the normal force. So on that diagram, you see this pulling into the gravity pulling into the board is blocked by the board with a normal force to prevent this thing from accelerating and snapping through the board. Out pushes the normal force. So F normal equals 33.9 newtons. And you could put a note that it's equivalent to the Fy. Okay? Now that I have the normal force, I can calculate the force of friction. Because force of friction I can find on my reference table here with, if I start at the top and I come down, I see here's the equation for the force of friction. Coefficient times normal force. So that's what I'm going to use to plug in to get force of friction. So now, the coefficient of wood on wood when they're sliding, what I need to do is I need to go to the front cover of the reference table right here, and on the lower right, we can see that we have wood on wood, and when we slide, it's, oh, wait a minute, right there, wood on wood. When we slide, it's not the static value, it's the kinetic value when they're sliding. In other words, the 0.3 is what I plug in right here for the coefficient. So that I get off the reference table. And then the normal force I have is 33.9. And so the force of friction right here on the diagram, if you multiply that out, you get 10.18. Okay, so that's the backward force, 10.18, and this is the forward force. So now, finally, I can use Newton's second law. So you see, Newton's second law, the easy law. Look at all the thinking that has to go before you even start plugging things in, okay? So, as I said, this forward force is the x component of gravity minus the force of friction all over mass. Now, you don't have to write this out because that formula is sufficient, but put it in your notes so you can hopefully, if you're confused about what I'm going to do with the numbers, you could look back here and see where things came from. So, as I said, the forward force is the 19.6 newtons. The backwards force of friction is the 10.18 newtons. All over the mass of 4 kilograms. And when you divide that out on a calculator, you get 2.35 meters per second squared. All right, so let me pause to give you a chance to catch up if you need it. All right, so inclined planes, see how hard that was, all those steps? So let's just look back and go over it again. So hopefully now that you have everything written down, you could focus more on the patterns here. Force diagram, gravity always straight down. Normal force, always perpendicular to the hill. And then friction directly up the hill. to figure out the acceleration, you've got to break gravity up into components. How much of gravity goes down the hill? All of it goes this way, but there's a part of it that goes this way. You make a right triangle like this. Now here's the original gravity vector. So this is one leg, the other leg, and here's the hypotenuse. Again, I would recommend possibly using a piece of paper to help you construct these, and drawing this as big as possible so that you're not cramming things in. You start cramming things in and you're really going to be in trouble here. So label this fx, fy, 30 degree there. Use the sine and the cosine to find those pieces, this being the opposite sine, this being the adjacent cosine. Once you have those pieces, you use the y as the normal force into mu f normal. And then finally, this is the x component right here, minus the force of friction, forward force, minus the backward force over the mass, and you get the acceleration, okay? Now, one final thing that I want to do is the acceleration if there was no friction. So maybe we have like a perfect sheet of ice and we put the wood block, or we put little wheels on it with zero friction or very little friction. So rather than erase this, I prepared a pre-calculation here. This is how the calculation would change. Let's see, maybe I'll go like this. Okay, and so we could see the force diagram and the old calculation. So take a moment and just quickly jot this down. If no friction, in other words, coefficient is 0, okay? So go ahead and copy this down. Okay, so notice now we still have the x component minus the friction, but the friction is 0 because there's no friction in our diagram. So our diagram would look like this, just two forces. And our calculation would then just be this x component, the 19.6, pulling this way, 19.6, minus 0 in the backwards direction over mass gives us 4.9 meters per second squared. So it'd be that out of the calculation. And you get more acceleration, obviously, without friction. So that was inclined planes. A simple situation analyzed with a simple law becomes complicated, okay? But I hope you got the big ideas about the calculation. If you're nervous about this, then let me just say this is very rare on the Regents, but it shows up once in a while. And so I have to show you how to do it. The other thing, even if it shows up on the Regents, sometimes all you have to do is draw the force diagram. That's all they ask. Or they ask you to recognize what's the correct force diagram on an incline. And then they might put another choice, normal force going straight up instead of a diagonal. They might put gravity going down the hill for another choice. And so you look at the choices, and maybe the only thing you have to do is pick the right force diagram among 4 choices. So it can be easy question, or they could have all this out in detail. But again, don't panic. It's not very likely, but we do have to show you how to do it. All right, so I hope you enjoyed the video. I'll see you in the next physics video.